Good morning, folks. How's it going? This is Mike coming at you with yet another video on Foundations of Math 2. And in this video, we are going to begin a brand new chapter, and we are going to begin talking about probability. Probabilities occur in just about every part of life. Fun things, games, some not so fun things like paying insurance. We have sort of our basic sort of common samples of you take a fair coin and you toss it. What's the chances that you'll get, say, a heads? Or you take a fair six-sided die and you roll it. What's the chances that you roll a six? Or something like that. Those are sort of the basic ones, the more sort of obvious examples that we would think of. But probability gets used a lot in many other facets of life. How much you're charged for your car insurance or homeowners insurance, things like that. Probability is being factored into those things as well in some way, shape, and or form. So probability is a very, very important topic to know, very important to understand a lot of calculations that are done for computing probabilities of things happening. But we'll be focusing more, for the sake of learning these formulas and all these things, we're going to be focusing more on those sort of more clear-cut and obvious real-world samples, where we're picking a card from a deck, or we're tossing a coin or something like that. And these types of things, when we do these things, they're called probability experiments. A probability experiment is a process that leads to well-defined results called outcomes. And outcomes are just results of a single trial of a probability experiment. Here's an example of a probability experiment. You're drawing cards from a deck of standard 52 cards, and each draw that you do is an outcome, and the card that you get from that draw is the outcome for that particular draw, or in a more mathematical sense, that particular trial. Your probability experiment could be taking a six-sided die and rolling it, and what you get as a result of each roll, that is going to be the outcome. So a probability experiment is sort of just a general description or general process of what you're doing. The individual results you get from each trial or each whatever you want to call it, those are the outcomes. And what we're focusing on in this chapter is we're focusing on probability experiments where we know what outcomes can happen, but we don't know which outcome will happen in each trial. We want to know what the possibilities are, but we don't want to know what is going to happen next. We don't want to know necessarily on each trial what is going to happen next. We can't see into the future, but if there was ever a case where we would know for every single trial what is going to happen, then that's not really fun. That's not really testing or computing anything with probability. And when this is the case, when we know what possible outcomes there can be, but we don't know what outcome is going to happen in each trial, then we say that the outcomes are random. So we want a random probability experiment here. So if we list all of the possible outcomes in the probability experiment, we're going to get what's called the sample space. So going back to our scenario where we take a fair six-sided die and we roll it, all the possible outcomes you can get are 1, 2, 3, 4, 5, or 6. So we take those outcomes and we write them in a set, each guy separated by commas. So we're using roster notation here. And this is the sample space. So as you see, sample space for the probability experiment of rolling a fair single six-sided die is going to be 1, 2, 3, 4, 5, or 6. If we had, say, a fair two-sided coin, if anybody has a three-sided coin, I'd be very interested to see what that looks like. But if you take a fair two-sided coin and you were to toss it 2 times, the outcomes you could get, well, you could get a heads on the first flip and get a heads on the second flip. You could get a heads on the first flip and then a tails on the second flip. You could get a tails on the first flip and a heads on the second flip. Or you could get a tails on the first flip and a tails on the second flip. So this would be the sample space for taking a fair two-sided coin and tossing it twice. We have 4 possible outcomes there. So that's what we're talking about when we talk about the sample space. And what we're doing when we're calculating probabilities is we want to know the chances of a particular outcome or particular outcomes happening. But in terms of math, what that's really saying is if we look at the sample space as a set, what we really want to do is we want to find the chances of having a subset of the sample space happen. So we're focusing on a certain element or certain elements of the sample space, and we want to know the chances of that happening. And this particular outcome or these particular outcomes is what's known as an event in the world of probability and probability lingo. So an event is any subset of the sample space of a probability experiment. So some examples, again going back to our example of rolling a fair single six-sided die. The event could be, say, rolling a number that's even, or it could be rolling a number that is less than 5. It could be rolling an odd number. It could be rolling a number less than or equal to 2. It could be the probability of rolling a 7, something like that. But that's just sort of our first basic introduction into the concept of probability experiments, sample spaces, events, outcomes, all those things. So now some basics on probabilities, their values, how these things relate to each other. The probability of an event happening is always going to be between or equal to 0 and 1. It's never negative. It's never greater than 1. And the probability of an event, or maybe it's just one particular outcome, is 0 when the event or outcome cannot possibly happen. And the probability is going to be 1 when the event or outcome is certain or guaranteed to happen. And if you take the probability of each possible outcome in the sample space happening, if you add up all those probabilities, the sum has to be 1. If your entire sample space, or if there's only these many things that can happen, and the largest, and the probability that something is guaranteed to happen is 1, then since we're guaranteed to have one of these certain number of possible outcomes, then the sum of the probabilities of each of those individual outcomes happening has to equal the probability that something is guaranteed to happen, and that's 1. So those are just some basic properties, facts about probabilities of events happening. What we're going to focus on in this video is 2 types of probability: theoretical probability and also empirical probability. And these things are not exactly the same thing. Theoretical probability is the probability that an event or outcome should happen every single time. Theoretical probability does not rely on trials, and it assumes that every outcome is equally likely. So this is without, say, flipping any coins, or without rolling any die, or without taking any cards from a standard 52 card deck, say. Theoretical probability is saying, okay, by doing sort of a basic calculation that we'll see very shortly, what are the chances that this thing happens? That differs from empirical probability, which is the probability that an event or outcome happens based on trials. So now we're actually rolling that fair 6-sided die, or we're flipping that coin, or we're actually taking cards out of our 52 card deck, and we are recording what the results are. We're recording what the outcomes are, and using another simple calculation that we'll see very shortly, we can calculate that probability of a particular event or outcome happening. So here's the formula for theoretical probability. Let E be an event in the sample space S. N of E is going to be the number of outcomes in the event E that have happened, and N of S is going to be the number of outcomes in the sample space S that have happened. So the theoretical probability of this event E happening is going to be P of E, that's probability of E happening, equals N of E divided by N of S. Empirical probability, if we actually run some trials, if we run, say, N trials in our probability experiments, and the frequency or the number of times that the particular event that we're looking at happens, if that number of times that this happens is given by F, then the empirical probability of E is P of E. This is equal to F over N, the number of times it happened divided by the number of trials that we had. And for theoretical probability, some notation and a nice little calculation. The event E prime, this is the event that E does not happen. Using our basic probability principles, P of E not happening, or P of E prime, has to equal 1 minus P of E. In the sample space, and in the eyes of a particular event, capital E, either E happens or E does not happen. The sum of those probabilities, probability of E happening and probability of E not happening, has to be 1. Because between those two things, something is guaranteed to happen. Probability of something guaranteed to happen is 1. So if I subtract the P of E from both sides of this equation here that we just said, if I subtract this guy from both sides, that's going to give me that formula right there. But now we're actually going to see some samples where we calculate the theoretical and the empirical probability of an event happening, and we're going to see how these things are not necessarily the same. So first up, a fair six-sided die is rolled once, and you do this 10 times, and the results of the 10 rolls are given here. You get 1, then 4, 3, 4, 6, 6, 6, 2, 5, and 1. Obviously, very, very realistic possibility here for the 10 results that you would get. What's the theoretical probability of rolling a 6? What's the empirical probability of rolling a 6? And then what's the theoretical probability of not rolling a number less than 3? So as we mentioned earlier on, in one of our previous sample problems, the sample space here, very easy. 1, 2, 3, 4, 5, and 6. Nothing complicated happening there. So the theoretical probability of rolling a 6, in this case, rolling a 6 is going to be our event E. And by our formula for theoretical probability, P of E is the number of times that E occurs divided by the number of outcomes you can have in your sample space. Well, we're just looking at our sample space for this. There's only a 6 that happens once. And we have 1, 2, 3, 4, 5, 6 guys in our sample space. So P of E, the theoretical probability of rolling a 6, is going to be 1 over 6. And if you convert this to a percentage, you get about 16.67%. This is rounded to 2 decimal places. What you actually get is 16.666666 repeating all the way through. So somewhere near there. But this is the probability of rolling a 6 without doing any trials whatsoever. This is just our basic knowledge of, okay, it's equally likely to get any one of those 6 numbers. There's only one number that we're looking for in our event. It's a 6, and there are 6 possibilities. So one guy that we want in our event divided by the number of possibilities, which is 6. Now, the empirical probability, so this was theoretical. The empirical, which I'll just put EMPIR for short, we did this this sequence of 10 rolls here. We have our results listed up here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 trials. So N is our 10. F, the frequency or the number of times that the particular event happened. Well, how many 6s do we have showing up here? 1, 2, 3. So it's 3 over 10. Or as a decimal, 0.3, or 30%. So we can see here that there is a difference between these two types of probabilities. Empirical and theoretical probabilities when you do this a finite number of times, and especially a relatively small finite number of times, you are going to see, or you can see, some significant variances or differences between the theoretical probability and the empirical probability of an event happening. 30% significantly different from 16.67%. But does that necessarily mean that these two things are never going to be even remotely close to each other? No, we're not quite saying that. What's giving us this significant difference between our empirical and theoretical probabilities is that we have a relatively low number of trials that we have done here. 10 in the grand scheme of probability and doing experiments and coming up with trials for things. In this scope, 10 trials is very, very, very little. If I were to do, say, 100 rolls or 100 trials, or say 1,000 trials or 10,000 trials, and if we recorded all of the results that we got from each one of those 1,000 or 10,000 trials, and we calculated the empirical probability of this same event of rolling a 6, then we can say with reasonable certainty, and I specifically word it like that, reasonable certainty, we'll come to something like that later on in the course. But we can say with reasonable certainty that this calculation here that we would get, if I did f over n, I would get a percentage that is significantly closer, if not almost identical to 16.67%. And this is a little bit of foreshadowing, but the more trials you do in any kind of probability experiment, the more trials you do, the closer the actual probability of the thing happening based on your trials, the closer that becomes to what we know we should get. The probability that we should get without having to do any trials whatsoever. So as the number of trials increases, empirical probability gets closer and closer to theoretical probability. So there's still one more part we have to answer here. What was the theoretical probability of not rolling a number less than 3? So if I say rolling a number less than 3 is some new event, I'll call it F. It doesn't really matter what you call it. So the probability of F not happening, or P of F prime, is going to equal 1 minus P of F. So F here is rolling a number less than 3. Well, if we go back to our sample space here, what are the numbers less than 3? 1 and 2. So there's 2 events, or 2 outcomes in our event, capital F, that I want. How many possible outcomes are there in the entire sample space? 6. So it's 1 minus 2 over 6, or 1 minus 1/3, and that gets me 2/3. So this is the theoretical probability of not rolling a number less than 3. Now, we could have worded this other ways. We could have said, what's the probability of rolling a number greater than or equal to 3? And then you could have come up with the same answer. So nothing really super crazy there. Again, this is a sample that's pretty familiar, that we're all pretty used to, but it does nicely highlight and showcase the difference between empirical and theoretical probabilities, and how for these low numbers of trials, these things can be significantly different. Second problem here, to wrap up our video, suppose you pick 5 cards from a regular 52 card deck, and we pick the following cards: the 5 of spades, the jack of hearts, the 9 of hearts, the 3 of clubs, and then the ace of spades. Calculate the theoretical and empirical probability of picking a diamond. So I'm actually going to let you guys try this one on your own. Pause the video here. Use the spirit of our last sample problem, as well as the definitions of empirical and theoretical probability, and figure out what these probabilities are each going to be for the event of picking a card that is a diamond. So once you think you have the answer, press play, and we will see if you were correct. Okay, so let's see if you came up with the correct answers. Theoretical probability. First up, theoretical probability, if we listed out the entire sample space, which in this case there's 52 cards, and we're not going to write out 52 numbers, but I think we can all sort of understand what the sample space would look like. The theoretical probability of us picking a card that is a diamond would be the number of outcomes in the event, that is to say the number of cards that are diamonds, divided by the number of possible outcomes in the entire sample space, that is the number of cards there are in the deck. So if this here is my event E, picking a card that is a diamond, P of E is, as we just said, the number of diamonds there are in the deck, 13, divided by the number of cards there are in the deck overall, 52. And 13 divided by 52 is 1/4, or 0.25 as a decimal, or 25%. That one I don't think is really going over too many people's heads. Now, what's the empirical probability here? Well, this probability all has to do with those trials that we did. We said that we picked 5 cards. Here's our formula for the empirical probability. We picked 5 cards, or we had 5 trials, so that's our n value here. And then f is the frequency, or the number of times that the event happened in those trials. But if we look at our cards, we picked a spade, heart, heart, club, and spade. We didn't pick any diamonds whatsoever. So there were 0 diamonds that we picked, so the event happened 0 times. It was out of 5 picks, or 5 trials, so 0 divided by 5 is obviously 0, or 0%. So again, significant, massive difference here between the empirical probability and the theoretical probability of picking a diamond from the deck. But as we said, looking at our previous sample problem here, the more trials we do, the closer and closer this probability would get to this probability here. Because there's only 52 cards in the entire deck, we'd only have to do 52 trials, and at the end of those 52 trials, these two probabilities would be exactly the same thing. But the more and more cards we pick, the more and more diamonds we are going to have. And when it's all said and done, once we've picked all the cards, we will have picked 13 diamonds out of a deck of 52 cards, and our empirical and theoretical probabilities will be exactly the same. So guys, that concludes our video here on sort of an introduction to probability. Just really getting ourselves familiar with some terms, outcomes, events, probability, experiments, sample spaces, and then comparing theoretical and empirical probabilities and seeing how they relate to each other in some sense. We saw how they can be significantly different, and then we also talked about as you increase the number of trials, these probabilities get closer and closer to each other. If you have any questions or comments, please be sure to reach out to me, guys. Emails, texts, phone calls, whatever you need to do. Until the next video, take it easy, guys.